Hello students, in the last session we did complete units and measurements chapter. The things that we have seen in the last session were significant figures, we did see that one. Then we saw like dimension analysis and then we saw propagation of errors, right? So those were the things that we have seen in the last session. In this session, as I've already told you, it will be like an extra part where we will do Vernier caliper and then the screw gauge, fine? So let's jump into it. Let's see what is meant by Vernier caliper. Vernier Caliper. As the name suggests, Vernier means it's the name of the scientist, okay? So that's Vernier. Then comes Caliper. Caliper actually means something that is attached to the main instrument is called as caliper, okay? Something that is clinging on to the main instrument, okay? So here what you will actually have is you will have a main scale to which Vernier scale will be attached, okay? So together I'll call it as a Vernier caliper, right? So let's see how to make measurement using that Vernier caliper, right? So here the construction is you have a main scale, right? So this main scale is actually a normal ruler, but extra thing is you will have a protrusion to it, right? I'll call it as lower jaw in this situation. As it is facing downwards, it is called as lower jaw, okay? To this main scale, you have a vernier scale attached to it. So this is the secondary scale, which is the vernier caliper, right? So to make the measurement, what I should do is I'll have to place the lower object. I'll have to place the object to the lower jaw in this situation, and then I'll just close it up, right? So I'll have to close it up such a way that there is no gap in between. So up to that, I'll be able to measure the distance of that particular object, okay? So this is considered as lower jaw. So lower jaw is generally used to measure the diameter, right? So outer diameter could be measured using lower jaw. Same way, it is not in the picture anyway. If you had seen that vernier caliper, you will know this one. So in order to measure the inner diameter, you will have an upper jaw, okay? So the upper jaw is exactly opposite to that of the lower jaw. So it is designed something like this, okay? You have a flat surface to the outside and then the curvy surface will be towards the inside, okay? So this is how you'll have that upper jaw. So what we will do is, we will place an object such that the flat position is facing the outside, right? So we will be able to measure the inner diameter in that situation. Got it? So here I am about to measure the outer diameter. Okay, both those things falls into the same understanding, but the thing is the design is something different. Okay, that is what you need to know. So in this situation, just the lower jaw is enough. With that, let's see how to find the measurement using vernier caliper, right? So here, with respect to the main scale, the minimum value that I could count is like 1 millimeter, right? In the normal centimeter scale, you will have the minimum value to be like 1 millimeter. That's the lowest possible value that I could measure using normal ruler. So here I'm going to add an extra vernier scale to it. So using the vernier scale, I'll be able to measure still more lower value. Let's see how least I could be able to count using vernier caliper, okay? So that lowest count that I could measure is called as the least number, okay? So we'll see what is meant by least count also, right? So here, when there isn't any error in this design, okay, so the design is perfect, which means there is no any error into it, right? So in that situation, let's see how to measure the value. Then we will see if there is error, how to overcome that error, okay? So that is something that we'll see next, okay? That too is easy. Those are called as positive and then negative error. We will look into it afterwards. First thing is, let's see how to measure using this vernier caliper, okay? So this, in the first situation, it is like zero error, which means there is no error in the construction of the device, okay? It is like perfectly aligned. In that situation, I'm going to find the measurement out of it, okay? So here you have a main scale, the above one, right? So the main scale is given here, and then on the lower side you have the vernier scale. That is what I have written here. So on the lower side you have the vernier scale. The construction is such that in the main scale we obviously know, so that is like a millimeter scale, okay? So for 1 centimeter you will have like 10 divisions into it, right? So obviously you are having 10 divisions, so up to this you have like 5 division, then you have the next 10 divisions, okay? But in the vernier scale, you are designing it in such a way that you have like 10 division in 9 millimeter itself, okay? So you will have like 10 divisions within that 9 millimeter range itself, fine? So in that situation, what happens is, like, every division in the vernier scale just gets offsets a little bit from the main scale reading, right? So that is how it's going to be. So how it is aligned is such that with respect to 1 millimeter with the main scale, you will have vernier scale such that that's going to be like 0.9 millimeter, right? Because obviously you will have like 10 division in 9 millimeter itself. So if I'm going to consider the first division, that's going to be like 0.9 millimeter, right? Got it? You should know this logic, because in 9 millimeter I'll be able to get like 10 division. Then obviously the first division of the vernier scale should be equal to 0.9 millimeter, right? That is what I have given here. So the first division is going to be like 0.9 millimeter. Got it? And then the gap between the first reading on the main scale with respect to the first division and the vernier scale will be like 0.1 millimeter, because the total distance is obviously 1 millimeter, and then the vernier scale division will be equal to 0.9 millimeter. Therefore that leftover space will obviously be like 0.1 millimeter. That's what I've written here, right? For the next division, which means the second division in the main scale, that will be like 2 millimeter. If I consider the vernier scale, it's going to be 0.9 for the first division, same way 0.9 for the second division, right? If I consider it together, it's going to be like 1.8 millimeter, but in the case of main scale, it's going to be 2 millimeter, right? So the in between gap will be obviously 0.2 millimeter, right? So this is how I'll design the vernier scale. Okay, so the design is something that you have 10 divisions for 1 centimeter with respect to the main scale. But in the case of vernier scale, you will be having like 10 division for the 9 millimeters. So that is how I'm going to design in this situation. So that interval between the main scale and the vernier scale for the first division will be like 0.1 millimeter. That's how I'm going to design this vernier scale. Now let's see the application of it, right? So when you move the vernier scale over the main scale, what happens is you just create in between space to it, right? In that in between space, I'll be able to put my object. That is how this construction actually looks, right? So from the diagram itself, it is pretty clear. As you move the vernier scale, I'll be able to place an object into it. Then I will tighten it to get the reading. Here what I'm going to do is I'm just going to move vernier scale little bit such that the first line in the vernier scale is going to coincide with the first line on the main scale. That's how I'm going to move it, right? So in the initial situation, when both the jaw was locked, 0 of the main scale was coinciding with the 0 of the vernier scale. That's how it's going to be. So now I'm about to move the first little bit movement. What happens is the first division on the main scale is about to coincide with the first division of the vernier scale, which means the gap that is created is equal to 0.1 millimeter. Okay, so that is how it is going to be, right? Obviously the first division is coinciding, which means the least count that I'm about to get here is like 0.1 millimeter. So the least count using vernier caliper will be like 0.1 millimeter in the situation that I have like 10 divisions, right? So we do have other vernier caliper where you'll have like 50 divisions, right? So we'll see that one also. Fine. So here I have like 10 divisions. So in this situation, the least count that I got was 0.1 millimeter. Fine. So here what I did is I was able to split that 1 millimeter into 10 parts, and the least thing that I was able to get is like 0.1 millimeter. That is what this actually represents. Okay. So if we move a little bit extra further, then what happens? The second division on the vernier scale will coincide with the second division on the main scale. So if I get a reading, that's going to be like 0.2 millimeter. So if I move extra a little bit, then I'll get like 0.3 millimeter. That's how it's going to be. Then there will come a point where, so you'll move to the next stage, right? So you'll get like 1 millimeter. So in that situation, this thing will completely move off, and then the 0 of this vernier scale will match with the 1 of the main scale. So in that situation, which means the gap is going to be like 1 millimeter. That's how it's going to be. Fine. So next comes is the error. Okay, so you have like two errors, which is called as positive error and then the negative error, right? So from the name, how we could actually do is, if it was given in the question as positive error, then we'll have to subtract it. Okay, so it is like another way around. And then if it was given as a negative error, then we will have to add it. Okay, let's see the logic behind it. So if it was a positive error, how does it that Vernier caliper actually looks is, with respect to the main scale, that is a fixed thing. So main scale, you will be having like 0 to 10 millimeter. That's how it's going to be. But if you look at the vernier scale, when the jaw is completely locked, the situation is such that, so after using multiple times, it might not be like properly fixed to it. Okay, so that thing will arise every time. So once you start using that vernier caliper again and again, what happens is there becomes some ridges in that inner jaw. Okay, so when you have that ridges, it will not lock completely. So in that case, you will have some error into it, right? So if you have an error, so how to rectify that error, that is what we are about to see here. So we are locked in such a way that the 0 of the main scale is in front of the 0 of the vernier scale. Okay, so it is not coinciding properly, as I've mentioned above. So here how it actually looks is, main scale reading is ahead of the vernier scale reading. Okay, that is how it is, right? So 0 of the main scale is ahead of the 0 of the vernier scale. That's how it looks, right? So this kind of error is called as like positive errors, because even though I have closed the jaw completely, still you get readings out of it, right? So this error is called as positive error because the jaw is completely closed. Therefore, the answer should be 0 because I didn't make any movement to it. But you get the answer as something, right? So here I get extra answers. So this is called as positive error. So from the final answer, I'll have to minus this value, right? So whenever you have a positive error into it, you'll have to subtract it, okay? So positive error arises when 0 of the vernier scale is behind the main scale 0. So when it looks something like that, so that error is called as positive error. So here we can look where does it exactly match. Let's make it this way. Here the third division of the vernier scale is going to coincide with the main scale, okay? So which means you have an error of 0.3. So that too is going to be positive. Therefore, I'll put a positive sign to it, which means you have like plus 0.3 millimeter error in it, okay? So the least count that I could actually measure is like 0.1 millimeter, but in this situation, when you lock it completely, the 0 of the main and the vernier scale doesn't coincide. So let's see the reading, okay? Where does it actually coincide? So that number will be the will be the error that you get while doing the measurement, okay? So here it is going to be plus 0.3, which means I'll have to subtract it from the value that I'm about to get, okay? So whenever they give you a positive value, we'll have to subtract it, okay? Then the other way around is like negative error. So vice versa case. So in that situation, I'll have to add it to the value that I'm about to get, okay? So here it is like other way around, which means with respect to the main scale, 0 of the main scale is behind the 0 of the vernier scale, okay? Which means 0 of the vernier scale is ahead, okay? In this situation, it's like other way around case. So here what I will get is like when both those things are completely locked, it doesn't coincide, fine. So when you start pulling it out, you get the value to be 0, then you start measuring it, right? So some reading is actually missing, so I'll have to add that to my final value. So this is like the vice versa case of the positive error. That's how it is. So much more extra explanation is not needed, okay? It should be obvious, right? It's the other way around of the positive error that we have seen above. So here let's see where does it actually coincide. So it coincides with the 8th division, right? Therefore the error in the second case will be like minus 0.8 millimeter, right? So here I'll have to add 0.8 to the value that I'm about to get. So this is how you'll have to measure using like vernier caliper, right? So these are something that you need to know. We have an experiment case that I've given here, right? So from this experiment, we'll just see how to measure the reading exactly, how to consider the main scale reading, and then how to add the vernier scale to it. So we'll see that I've given below. So this is how we make measurement from the vernier caliper, okay? This should be known. Now what I'm about to do is I'll create a formula for the least count, right? So you'll be able to get two formulas. Let's see the first one, right? So first one is actually the explanation that I've given to you. That is like I'll have to subtract one main scale reading from one vernier scale reading, okay? So leftover distance will be the least count in the situation, right? Therefore, the first formula is like one main scale reading minus one vernier scale reading. That will give me the formula for the least count, right? In the first situation, one main scale reading was equal to 1 millimeter, obviously, and then one vernier scale reading was equal to 0.9 millimeter, right? So what should be the least count in the situation? It should be equal to 0.1 millimeter. That is what I have got, right? So that was the explanation that I gave while doing this thing. So you should be clear with this one. Next formula depends on the design of the vernier scale, right? So in this situation, you got like 10 division in the vernier scale, right? Such that I had an offset of 1 division with respect to the main scale, okay? Which means 9th division on the main scale matched with the 10th division on the vernier scale. That is how I constructed it. So in order to get the second formula, how I should consider is, I'll have to consider the number of divisions in the vernier scale, okay? So the formula you'll get is actually 1 divided by, fine, number of divisions on the vernier scale, okay? Vernier scale, that will be the formula, right? So least count here will be like 1 divided by number of division on the vernier scale, okay? So here if I do the math, I'll have like something like this: 1 divided by number of divisions on the main scale is going to be like 10, okay? So the least count that I'm about to get here is like 0.1. So what was the least count with respect to the main scale? It was equal to millimeter, okay? So I'll have to use that unit, which will be like 0.1 millimeter, fine. So here the main logic that you need to know is, vernier scale should be offset by one division with respect to the main scale, right? That's how I got it, which means ninth division on the main scale coincided with the 10th division on the vernier scale. So that is how it was built. Okay, when you have such a type of construction, that is how we generally build the vernier scale. So when you have such a type of construction, the universal formula that I could use is like 1 divided by number of divisions on the vernier scale, because that will be easy for us for understanding it. Okay, but in the situation least count 1 MSR minus 1 BSR, in that situation I need to know the distance. What is like 1 BSR? 1 MSR is something that is known because it is always like 1 millimeter. But in the case of BSR, I should do the imagination to get that answer. But if you use this universal thing, 1 divided by number of division on the vernier scale, I'll always get the least count correctly. Okay. So you have like other one vernier caliper which is also generally used. In that situation, I'll design it such a way that you have like 49 divisions on the main scale, right? So 49 division on the main scale actually means like 49 millimeter on the main scale. Same way you have like 50 divisions on the vernier scale. Fine. So you got like 50 divisions on the vernier scale, which is going to coincide with the 49th division on the main scale. So 49th division on the main scale is obviously 49 millimeter or like 4.9 centimeters. So that is how I'm going to design that scale. So it will look like a larger one when compared to the 10 division thing. Okay. So here if I consider it that way, so it is hard to use that first formula, which means like 1 MSR minus 1 VSR is like hard, but the second, this formula will be like handy, right? So here for the second one, it will be like 1 divided by number of divisions on the vernier scale, right? So number of divisions on the vernier scale is obviously like 50 in the situation, right? So 1 divided by 50 will be equal to 0. If you do the math, you'll have like 0.02 millimeter. So if you do the consideration between the above scale, which is like 10 division scale, to this 50 division scale, with respect to 10 division scale, how it actually propagates is first minimum value will obviously be 0.1, then it will be like 0.2. That is how I'll count, right? 0.1, the next reading that I can get is like 0.2, the next one is like 0.3. So it goes in such a fashion. Okay, but if you consider the 50 division scale, the first reading that you are about to get is like 0.02. Okay, the next reading will be like 0.04. Okay, it goes in the multiples of 2, right? And then the next reading that you will get is like 0.06. Okay, you will not be able to get that odd numbers, which means like 0.03 is not possible for us to measure. Okay, and then 0.05 is also not possible for us to measure. Okay, so if you want to get those number also, what you should do is you'll have to match 100 division of the vernier scale with the 99th division on the main scale. So if you match in such a fashion, then I will be able to get that odd numbers also, but that is not generally used. Okay, so 50 division scale itself is very big. So in order to design like 100 division scale, that is like not needed, by the way, right? So 50 division scale is something that is used in engineering application related stuff. Okay, so this is also another one scale which you need to know, right? So here you have the least count to be 0.02 millimeter. Next, let's measure the reading from this vernier caliper. Okay, so this is like a question that I have written here. So here first I'll have to measure the vernier scale reading, right? So in order to measure the vernier scale reading, what I should do is first I need to know where does the zero of the vernier scale coincides with the main scale. Okay, that is something that I need to know. So to get that value, it is like this one is like 2 centimeter, or I'll be able to tell it as like 20 millimeter, right? So this is like 20 millimeter, then comes 21, and this is like 22, and then it is in between of 22 and then the 23, right? So I'll consider something that is ahead of it, ahead of the vernier scale reading, which is going to be like 22, right? So the main scale reading that I'll get in this situation will be like 22 millimeter. Fine, now I have got the main scale reading. Then let me check what is the vernier scale coincidence, right? Obviously they have given it in red color, which is matched with it. So here for convenience they have given it in red color. In the question you'll get that value itself straight away, right? We will do such a kind of sum. So let's see what that reading actually is. So here the reading is actually 4, right? So vernier scale coincidence in this situation will be like 4, right? So the vernier scale coincidence in this situation is like 4, right? So in order to get the vernier scale reading, what I'll have to do is I'll have to multiply this 4 with the least count, right? So the least count here is like 0.1 millimeter, because this is like 10 division thing. If it was like 50 division vernier caliper, then I would have chosen 0.02 millimeter as my least count. In this situation, it's just only 10 division vernier scale. Therefore, I'll choose 0.1, right? So if I do the multiplication thing, 4 into 0.1, right? 4 into 0.1. So this will give me the answer to be like 0.4 millimeter, right? So now I have got that extra one division into it because the main scale could measure only the millimeter stuff. So that in between distance couldn't be measured. That is the reason why I used vernier caliper to it. So when I used vernier caliper to it, I just found the coincidence. Then what I did is I multiplied it with the least count with respect to that vernier caliper. In this situation, it was just 10 division vernier scale. Therefore, I multiplied it with 0.1, which I got to be like 0.4 was my answer, right? So the reading that I should get is, which is equal to 22. Okay, then I'll have that extra one decimal place that I found here, which is going to be 22.4 millimeter. Fine. This is the advantage of using vernier caliper to the normal ruler. Okay, the normal scale could find only 0.1 millimeter as its least count. Okay, when I add an extra apparatus to it, which is like a vernier caliper, I'll be able to divide that 0.1 millimeter into 10 divisions, right? So here I'll be able to find that extra one decimal into it, right? So this is how you'll have to use vernier caliper, right? So this is how we measure readings out of vernier caliper, right? You should be clear with all those things that we have discussed. Next, we will see screw gauge. Screw gauge is actually a simple mechanical device. The construction of the screw gauge is also simple, by the way. So what you actually have here is you have like a U-shaped frame, right? So you have an U-shaped frame and then you have a stud over here, right? So you don't want to know all those names. The thing is like, how does it work? That is what you need to know. So here you have a stud, which means you have like one end which is like fixed, right? The other one is the screw, right? So this screw will be able to move forward and then the backward, right? So it will be able to unlock, lock and then unlock, right? So when it is completely locked, I should get the reading to be 0. When I unlock it slowly, which means when I unscrew it slowly, I'll get the gap in between to it, right? So when I get the gap into it, I'll be able to place the object for which I'll have to measure the reading, right? So that is how it is going to work. So here you have a screw which will be able to move forward and then the backward. So to control the screw, I have a hollow cylinder to it, which is called as thimble, right? So this thimble, I'll be able to move it clockwise or in anti-clockwise direction as usual. When you move it in clockwise direction, you will tighten it, okay? You will lock it. When you move it in anti-clockwise direction, you will be able to unlock it, okay? And that will be the time where you'll be able to fix an object into it, for which you'll have to measure that length, right? So that these are the things that you need to know, right? So you have a stud, which is like fixed, and then you have a screw, right? Which is like a movable thing. In order to control the movement of the screw, we have this thimble, which is called as hollow cylinder, whatever it is, right? So this ratchet is something, an extra mechanism which is at the other end of the screw gauge. You do not want to know much about this ratchet, okay? So to tighten it properly, you have this ratchet. That's it, right? So then you have this main scale and then the circular scale, right? So we'll be able to get the reading from this main scale and then the circular scale. So that's how it's going to be. So this is the construction that you need to know, right? The one trick that you need to know is like pitch. There is something called pitch which you need to know. So this distance between one thread to the next thread is called as pitch, okay? So that distance is called as pitch. So here in this situation, generally in this situation, this pitch distance will be equal to like 1 millimeter. That's how we are going to design that pitch, right? So if I'm going to unscrew it for like one full 360-degree rotation, it moves in the situation. I'm going to unscrew it, therefore it just moves apart by a distance of 1 millimeter. That is how the design is going to be, right? So obviously this pitch in majority of the situation, this will be equal to like 1 millimeter. So when I'm going to unscrew it for like one rotation, there will be a movement of like 1 millimeter from the stud, okay? So you'll have that 1 millimeter gap into it, right? So if it is like 1 millimeter gap, which means the object that I could place in between that gap will be equal to 1 millimeter. That is how I'm going to design this stuff, right? So you should be able to understand this one. So pitch is the distance between the two threads. Generally it will be equal to 1 millimeter, but that's not the case in every single situation, okay? So here how I am about to design this one is like, when you have no error into it, so that's the first one, okay? Which means no, when you have no zero error into it, which means no error into it, obviously the zero of the circular scale, so here I'll call it a circular scale, right? So zero of the circular scale will coincide with the zero of the main scale. So that's how it's going to be. So when you unlock it completely, the zero of the circular scale will coincide exactly with the zero of the main scale. That's how it's going to be, right? So when I'm going to unscrew it, what actually happens is you'll start getting the readings out of it, right? So when I'm about to unscrew it, the zero will just go down and then you'll get the numbers. That's the distance that I have got between the stud and then the screw, right? Now what I need to find is the least count. in order to get the least count, the formula that I'm about to use here is like pitch will be given in the numerator, right? I'll explain it in a minute. So pitch will be in the numerator. Same way in the denominator, I'll have the same thing, right? There I had like number of divisions in the vernier scale. So here it will be like number of divisions in circular scale, right? The other way around. So this is what I'll have in this situation, circular scale. Okay, so what is meant by pitch? So pitch actually means the distance between through two threads. So in this situation, if it was like equal to 1 millimeter, okay, let's consider if it was equal to 1 millimeter, and then number of divisions that I could have could either be like 50 or it could be 100. It could be more than that also, but these two are the generally designed screw gauge. Okay, so here the pitch, let's consider it to be like 1 millimeter. They'll give that reading. Okay, so let's consider in that situation to be like 1 millimeter, and then number of divisions on the circular scale to be like 100, right? Then least count will be equal to 0.01 millimeter, right? So for pitch to be 1 millimeter, then in that situation, if I have the circular division to be 100 divisions, then the least count in that case will be equal to 1 divided by 100, right? Obviously it's going to be like 1 divided by 100, which will be like 0.01 millimeter. Okay, that's how it's going to be, right? You should be able to understand that logic. So for that one movement, if the first division coincides with the main scale, then the reading is going to be like 0.01 millimeter, right? So in this situation, I just split 1 millimeter into 100 divisions. Okay, in the last vernier caliper that I did study, I was able to split it into like 1 by 10th or like 1 by 50. That was possible. Here it is constructed in such a way that I'll get a more accurate value for like 100 division split for 1 millimeter, right? So that is how it's going to be. So here for 100 division thing, the least count will be like 0.01 millimeter. Next, we will see positive zero error and the negative zero error. Okay, see, positive error and negative error both are just the same thing. The thing that we have seen in the vernier caliper, we'll see the same logic here, right? So as we have seen in the vernier caliper, same thing applies here also. The way for positive error, what I should do is I'll have to subtract it from the measured value. Okay, same way if it was like negative error, I'll have to add it. Okay, so same thing will be applied here also. So in the case of positive error, what I should do is I'll have to subtract it. Okay, in the case of negative error, I'll have to add it. Okay, here I didn't consider like 100 division scale in this situation. In this situation, I considered 50 division scale, circular scale. Okay, so the least count that I could measure is pitch divided by number of division. Let's consider pitch to be 1 millimeter itself. So here least count will be equal to 1 divided by 50 millimeter, right? So if it was like 1 by 50, I'll get like 0.02 millimeter. Now I'll consider the first case, which is like the positive error case. Okay, so here the zero of the circular scale is below the zero of the main scale, right? So that is how it is, which means in this situation, when I'm about to unscrew it, I'll get extra values out of it, right? Obviously, right? Because here the second division is already matched with the main scale. So I get the answer like two coincidences has already happened. So when I'm about to unscrew it, I'll get that extra two coincidence, right? So I'll have to subtract it, right? The way I explained in the vernier scale, same thing here. So this is like a positive error, fine. So in the second case, what actually happened is the zero of the circular scale is above the zero of the main scale, right? So when I am about to unscrew it, then comes the zero, after which I'll start measuring the value. But here these four values are already need to be added to the measured value, right? So this is considered as negative zero error. Okay, same logic that we have seen in the vernier caliper, we are going to use the same thing here, right? So the logic is something same, right? When you get a positive error, subtract it. When you get a negative error, you just add it. In the case of positive error, zero of the circular scale will be below the zero of the main scale, right? In the case of negative error, zero of the circular scale will be above the zero of the main scale. So that's how it's going to be, right? Let's see for the second situation, which means negative zero error. Let's see the coincidence, right? So the coincidence is obviously going to be like 1, 2, 3, 4. So fourth division got matched, right? As you start unscrewing it, you'll have that fourth thing that is missing, right? So I'll have to add it to it. Okay, so this is obviously a negative error. So the circular scale coincidence here is like 4. Fine. So what is the circular scale reading that I'm about to get in this situation? The circular scale reading will be like 4 into the least count, which is going to be 0.02 millimeter, right? So you'll have like 4 into 0.02 millimeter. Okay, so the answer that I'm about to get here is like minus 0.08 millimeter. which means I'll have to add this negative error to the value that I'm about to get after measuring it, right? After measuring an object that I've placed between the stud and the screw, right? So these are something that you need to know regarding the screw gauge. Fine. So now if you had found this negative errors or errors into it, it's the same way. What how you should do is you'll have to find first the main scale reading. So once you got the main scale reading, then you'll have to find the circular scale reading, right? When you get the circular scale reading, just add the way we did it with the vernier caliper. So same thing, you just add both those things, so you'll get the reading out of it, the value, the length, the length of the object that you have placed between it, right? So when you have got that reading, what you should do is, if it was like negative error as we have in this situation, then I'll have to add this extra value to it, right? If it was like a positive error, then I'll have to subtract it, right? The same logic, whatever we applied with the vernier caliper, you do the same thing with the screw gauge, and then you'll get the reading. Okay, so these all are the things that you need to know regarding the vernier caliper and the screw gauge. As I've already told you, you get questions from this vernier caliper and screw gauge, right? Last couple of years, like last 4 years, you got questions from vernier caliper and screw gauge. Okay, you get at least one question from these two topics, right? So the thing is, it's going to be an easy question. The thing is, you should know how to measure reading out of it, right? So you should be clear with all those things that we have discussed in this class. With this, the session gets completed. Bye.